Proceed. All right. So welcome to Physics 1405. This is our week 2 Zoom meeting. We're going to mostly focus on questions. Whoever's here can ask whatever they're finding difficult. But I am going to start out really quick with a demo on using a spreadsheet because we have some graphing in our lab this week, and we've seen in the past a lot of people struggle with the graphing. So I want to show you guys how to use the computer to graph. It usually gives you much better results than, we do provide graph paper for you if you choose to do it by hand, but most people get much better results. So if you are not familiar at all with using a spreadsheet, we're just going to start you out from scratch. I'm going to be using Google Docs because that is most universally available. If you use Excel, you should be able to get that through the college. You should have access to it already. Sometimes we provide some lab materials in Excel files or doc files, similar products. If you prefer to use Excel, you may. I'm going to just use Google Drive because that's something that people have access to for free. So you guys can see my Google window here. Yeah. I just go to drive.google.com. And this, of course, is my account. It's going to be populated from my stuff. But as long as you have a Gmail email account, you've got one of these, even if you've never used it before. So we go to new, and we're going to pick sheets. Some people have never used a spreadsheet before, but this is how you get one. All right, so this is our untitled spreadsheet. I'm going to name it, we're going to pause for a moment while it figures out what it's doing. You don't need to name it, but we're going to call it the graphing demo. All right, so your graph for this week, and it kind of provides you with a table. And one thing to note, when you do your table in the graph this week, you're going to be doing a projectile motion lab where you shoot things and you write down some data for what happens. There's going to be multiple columns in the table. You need to make sure that you're recording the data it's asking you. And then when you graph it, you need to make sure that you choose to graph the data it's asking you to graph. So this week we have a launch. Launch angle, time of flight. You notice that this parentheses seconds here, that is putting units on everything in that column. So you don't have to write, 2 seconds, 3 seconds, 4 seconds as you get your data. That little S up top is giving you your data and range in meters. Okay, so this is what your table looks like. And it gives you 25, and this is already given you in the lab. Now, one of the cool things about spreadsheets is once you get going, you don't have to type this all out. The spreadsheet asks you to go all the way up. I mean, the table in the lab asks you to go all the way up to 65 degrees. So I just highlighted the first few that I did, and the spreadsheet thinks a little bit and keeps track of what I'm doing and tries to guess what I want. So I highlighted this. You see the little blue box down at the corner. I'm just going to grab that and I'm going to pull, and it's going to fill in all the other numbers for me. Up. This is how much data the lab is asking you for. Okay, so time of flight in seconds is just how much it's in the air. And as you do each of these trials, you will set your little virtual cannon to each of these different angles, and then you will check. You'll shoot it. You'll see what happens. So you get a measurement for the time of flight it's in the air and for the range. Now, it asks you later on to graph range versus time of flight. So we're going to ignore, for the spreadsheet, we're going to ignore time of flight, and I'll show you how to delete things. If I click on the head of this column right here, and I right click, you can see I can just delete the column. Now, the default for making a graph is to have this very first column be your X variable, the thing that goes on the horizontal graph, and the second column to be the Y variable. So if it says in your lab graph range versus launch angle, you would make sure that the range is right here, the launch angle is right here, The first thing in that phrase is the thing that goes on the vertical axis. The second thing in the phrase is what goes on the horizontal axis. So I'm going to make up some data here. This is not going to be exactly the data you're going to get, but I'm just going to make up some data so we can see what a graph would look like. Okay, so say that we did our experiment and we got those kind of ranges. Now, making a graph is pretty easy. I'm going to highlight the data that I want. So this X and this Y is just extra stuff up here that I put in as I was describing to you all what this does. But if I include my labels in my highlighting, the spreadsheet will say, oh, hey, those must be the labels for her axes. And it will actually use that to label my graph for me, so I don't have to do it manually. So I highlight my column headings and I highlight all of my numbers. And I go up here to the insert menu and I insert a chart. Okay, you see that it's inserted the chart for me. I'm going to move it over and just grab it up here. You can see my cursor turns into a little hand. And you see that I've got some stuff going on over here that I can change if it guessed wrong. Though if you choose to set up your columns that way, to have them next to each other, put the X variable in the first column, your spreadsheet's usually going to guess pretty well. If your data is a little more chaotic than that, if you reverse it, you may have to change these things. So you see that it shows me that I have the first column on the X-axis, the second column on the Y-axis, and I can check or uncheck some of these options. Now I'm going to show you guys how to use a trend line. Our data for this lab is not linear. You can see it's not shaped like a straight line. This is pretty true. This is the basic of the shape that you'll get from the lab, though of course it will be based on your data. But I'm going to show you how to put a trend line in because you will need that for later. So if you go to this customize, I believe it's under series. You see under customize, under series, there's this little box called trend line. Now ours is going to be kind of meaningless because our data is not linear. But if you put that in, push the check mark, and you go down here to label, and you say use equation. That's something that you will need to know for the future. Okay, when I say use the equation, the label, this right here is numbers associated with this line that it uses to characterize your data. Now, because our data is not in a line, it's just kind of tried to give us an average of all the data we put in. But you guys need to know how to do that. So we don't need it for now, but that's where it is. You guys can put it in later. So we're going to uncheck that because we don't need it. But next time, if it asks you to find the slope of your line, that's how you do it. Okay, so for today, I showed you guys just basically how to put your data into a graph, how to create your graph. There's also options, you can create a little line that connects your data points. That's not very important for this time around because it's not linear data anyway. So you can see in this, my data, that it kind of starts out low and it kind of goes up to a peak and it goes back down. And this agrees with my numbers. So when you guys do your lab, you'll find that you need to be able to tell what the maximum angle, what angle down here on the x-axis gives you your maximum value up here in your data. So you look across, you find the maximum one, or for example, if two were even and you can tell that the kind of peak of the shape that you get, the kind of rounded curve, if you can tell that it's between the two of them, you can guess, oh, maybe my maximum is at 42 degrees because it's right near between my 40 data point and my 45 data point. But the way I did this, peak is right on 45. And so you would say, oh, my maximum range, the maximum of all of these data points occurred right here. And I can look down my data and say, oh yeah, 3 got up to 3.6. That was my maximum data point. So those are the sorts of analyses that you're going to be doing this week. That was the main point, the main thing that you guys need to know. just because graphing by hand is something that's really problematic. We end up with some kind of interesting results. And this is going to be a lot easier for you guys. So at the end, when you're done, you just have it. So your graph is there. I can see it. If you needed a line or an equation or whatever, like you will in future labs, you make sure all of those are showing. And then you can just go to File and down here in Print. And you can see, like, you can adjust how big your print thing is, make sure everything's on there. And you can choose, as a printer, this option that says Save to PDF. This will make it in the ideal format that you can submit it to me as a file. At that point, you can name it whatever you want. It will save as a file on your computer, and you can submit it in Canvas, and you'll have it. Okay, so I'm going to cancel that. All right, so that's the end of my demo. That's what you guys need to know for learning how to graph. And from here on out, we can just go on everyone's questions. So what did you guys find this week in your assignments?
I have questions on number 3 and number 5 of the lab. Hold on, I'm sorry, of the homework. I use the equation for impulse on number 3. And so I multiplied the 859 times 4.51.
Okay, so just remember, everyone else who might be here with us or watching this video later isn't familiar with the questions. Can you tell us basically what it's asking?
Let your car have a mass of 859 kilograms. Your car is moving at a speed of 4.51 ms when it strikes a parked car and stops in 0.17 seconds. What force did the parked car exert on it to stop it that quickly?
Okay, so we have a known mass, and everyone just be aware that everyone might get different numbers. So your numbers might not be exactly the same as someone else's numbers for this problem. Just be aware of that. Well, we have a known mass, and then what else do we know? We know velocity.
4.51, and then it also gives you the time, 0.17.
Okay, so we'll take your numbers. So these 3 numbers are known. And then the thing that we want to know is force. That's our unknown. So give us your numbers again for M and B.
M is going to be, that's kilogram, isn't it?
Yes.
859. 859.
Okay, what did we have for V?
4.51.
4.51. So actually, given that everyone's going to have different numbers, it's always also strategically better to solve by symbols first in our variables and get a formula for our answer, and then to plug in our numbers anyway. So what formula did you decide to use?
The impulse formula. Impulse equals the force times the time.
So impulse equals force times time. And what else does impulse equal to?
That's all I put on my end. And then I divided by the seconds.
Yeah. So what value did you get for impulse then?
22,788.763. And then the units I used for that was N.
Okay, so remember that N newtons are our units of force right here. So if you've multiplied something together, then that's not it. So the other thing that we want to get at this, your FT is equal to your change in your momentum. So delta P, which is, what is P again? P is mv. So this is m delta v. So whatever that number that you got it by multiplying your velocity together, right? with your mass.
Mm-hmm.
So the velocity that your car was going at went down the street at a certain MV, and you went down to 0 velocity. So your change in momentum was from your initial momentum to 0. So your total change in momentum was just however much momentum you had to begin with. And then you know that that's equal to F times time. So your momentum change in velocity is just equal to your initial velocity is equal to F times T. So if you divide both sides, because you know T, but you don't know F. All right, so is that basically what you're getting? Mass times velocity divided by time?
Mm-hmm.
Okay, and did you have any trouble with that answer after the fact or something?
I put it in the system and it didn't take it. I tried doing 22,789, like rounding up. I tried doing 22,788, and then I tried doing 22,788.76, and it didn't, the system didn't take the answer.
Okay, so in general, I mean, I would have to look at your specific answers to see, but let's just double check the math. I'm typing this in off screen. Okay, so M times V divided by T. So yeah, 22,788 is what you said that you got. Is that what you said earlier? I think Jasmine might be frozen. Okay. So we will wait to see if she reconnects or something. The answer here that I get if I multiply it out, which like I said, everyone's going to have slightly different numbers, so this is not going to be everybody's answer. So 22,788.7. Okay. So the question is, and I can't see exactly what the system wants from here, but the question is, what's our best answer to give the system? So I have seen it just take like big long numbers, but correctly, like if we did this in the laboratory, we would need to look at our initial data. So we have 3 significant figures on our mass. We have 3 significant figures on our velocity, and 2 on our time, though it might have given us a 0.0 or something. So the best result that we could technically for a lab result give is 2 significant figures here. We would want to round it to this number. For our homework, it's usually better and safe just to give 3 significant digits. So I would round it to this number and call it, oops, 22.8. And also the other thing I think is what a lot of people do is this homework system oftentimes does metric things to the units. So this is the number, but we also need to look at the units. So what are the units of impulse? Well, we can look either at this. This would give us newtons times time. And what's inside a newton? It's kilograms meters per second squared. So, and this right here is also kilograms times meters a second. If you have kilograms in over here in your FT, you have kilograms meters per second squared in your F, and you've times that by seconds T. So this has the same units. So this is the units that you want. Over here, kilograms meters a second. And it may, when you put the units in, you may discover that it's gone up to, times 10 to the 6 grams meters per second or something like that. These should be your safe units, but sometimes you might discover that it's changed the units. Usually if you had like a kilometers, I think is what I've seen it do. You calculate something, it's so many thousand meters and it changes it to kilometers. So when you choose that unit, you need to make sure that your numbers also agree with the unit it's asking for.
Yeah, because it didn't count my units wrong. It counted just the number. So I don't know. I don't know why. Well, I know why now, but I mean, I could go back and switch the units.
Okay, so if you didn't put these units in, you should have gotten your units wrong. And it may be that that's the part that you've got partial credit and that you've actually got the number right, but the unit's wrong. Is that agree with what you're seeing?
But whenever the units are counted wrong, doesn't it highlight it in red?
I'm not quite sure because my view is different than the student view. So I don't know exactly what you're seeing, but I can
Yeah,
also,
that's normally what I've noticed.
all right. So these are the numbers. So if you did it this way, you're doing it correctly. So at this point, go ahead and email me and I will log in and look at your specific responses and see why this is counting you wrong and what it's expecting from you. If you ever feel like you did the problem, if you feel like you did the problem right and you're getting completely counted wrong, in general, I said you guys could do this last week because we're still getting used to what the system wants. But if you just really feel like you keep getting it wrong and it won't give it to you, even though you have it right, you can email me and I will check and see why it's doing that. But this is how we do the problem. It looks like you had that part right?
Yes.
Okay, so great. We understand the problem and now it's just the system. So go ahead, those sorts of issues you can email me about and I will answer you specifically and directly with what the system is doing. All right, thanks for the question. Does that address everything that you're concerned about on this one? It seems like the concepts were fine.
Yes.
Okay, great.
Thank you.
Any other questions?
One more question, but I can wait if anybody else has a question.
I had the same question as you did, Jasmine, for 5, the elevator. Is that the one that you're asking as well?
Yes.
Okay. All right, well, go ahead and bring up the question and we will discuss it. So
Do you want me to read it, Daisy?
Oh, okay. So the question was for the homework, question number 5. The question's as an elevator releases 11,11700 joules of gravitation potential energy, while the screening 6.00 meters between floors. How much does the elevator weigh? So we're trying to find for weight.
Okay. So you're given a value for, can you read me your number again? Because mine will be different.
Yeah, it's 11700 joules.
So, and our height was 6.00. The 0.00 is more important than for sig figs than anything else. And then the thing that we're looking for is, and we're going to go ahead and write weight out because big W sometimes means other things besides weight. So the weight is what we want. All right, so how did you guys approach this at first? Like, where are we going?
So
You can go with that. I'm sorry.
no. Go ahead.
Well, I think maybe the equation that I used was wrong because I did PE equals weight times height.
Yeah, that actually works out. And normally you guys are going to see, actually, I think that they usually call it U in this book. So I'll back up and use U. So gravitational potential energy is equal to mgh, and weight is equal to mg. So this mg is common between the two. So U is just your weight times your height. So in this case, when we have energy and height and we want weight, then we just get your weight is equal to your potential energy divided by your height. So is this what you got when you did it?
So I did plug in the MGH part, and then so on mine, I ended up dividing the joules that was given by the M that was given, and then the units for the answer that I used was N.
Okay.
But yeah, my numbers are different, so the answer that I got won't be the same as what Daisy got.
Yeah, so a joules, remember that joules are the same as Newton meters.
Mhm.
So yeah, you will come out once you divide it in units of newtons, or remember that newtons have kilograms meters per second squared inside of them. So that would also be valid, but probably they will only give you a choice of one valid unit and the other units will be wrong.
Yeah, I think they add on there like KN to include the kilograms part.
Yeah, so a Newton, 1 Newton is 1 kilogram times meters per second squared. So when we've multiplied this out, a joule is actually 1 kilogram meters squared per second squared. And you guys can see that kind of right here. If we have, I'm going to change colors. If we have our weight in newtons and we multiply that by a height, then technically we've got all of this inside. Your height went into this meters squared. So you had just a meter, you multiplied it by height, you got meters squared per second squared. But these are just the short versions of those two units. So yeah, for your weight, a weight is just another flavor of force. Force has units of newtons, which newtons have all of this in, but once you've recognized what they are, you can just say a newton. So these are the two units that we have in this problem. And basically the connection between the two is just meters. There's a difference of a meter here. All right, so is anyone? Huh?
It's Jasmine. I have a quick question. Can I just send you what I have worked out?
What format is it in?
It's basically what you did, and then it gave me an answer, but the system, again, it's not taking it.
Okay, yeah, so that's another thing. Send it to me in an email and I will just check the system and see what it's getting from you and what it's expecting. And I can email you back about the details, like the difference. Is anyone else having that same problem?
Yeah, because I put that as my answer, what you got, and it still counted it wrong. So I thought I was doing something wrong, and I put the units KN because it doesn't give you an option just for an N, I think.
Yeah.
It should. Okay,
So
is anybody else waiting for any different questions on this particular help session? Okay, if nobody else is waiting for anything, I'll probably stop the recording and I'll go in and check and see what the difficulty is. Or maybe I'll go ahead and stop. If there's no more physics questions, I'll stop the recording. But since you guys are just here and you have the same question, I will log in to Wiley and see if I can tell what the problem is. All right, so everyone who's watching the video, thanks. Hopefully also you guys, maybe I will look at lab 2 really quick. I've already made an announcement on the graphing and kind of giving you guys some direction on the graphing. That's the main issue this week. The errors that we usually see are people who just don't really graph it very well or give me something else. So if you can do the graph, you can identify where your peak is. I probably will talk a little bit generally about projectile motion. Do you guys feel like projectile motion is something that's fairly clear and easy to understand? I will do a little presentation on that and then we can end the recording and then I will go check and see what the Wiley system is doing about your homework. So, okay. So I'm gonna just draw a little bit. When we shoot something or throw something up in the air, it has an initial velocity. Velocity is a vector, which just means something that has a magnitude and a direction, and we can represent it by an arrow. And there's two things that are happening to it once it's in the air already. In the horizontal direction, technically, and we're going to neglect air resistance for the most part, but in the horizontal direction, if we just threw something horizontally, it would just keep going forever and ever, right? The velocity at any given point would just be the same. It would keep going. If we throw something vertically up in the air, it's got to deal with gravity, right? So at first, it's going to have this big Actually, let's use a different color. It's going to have some big initial velocity in the y direction. Yeah, touched the wrong thing. Now it's trying to. And then the next second, that velocity is going to be reduced, right? And then the next second after that, that velocity is going to be tiny. And eventually it's going to go up and up and up until all the velocity has been stolen, right? However much initial velocity it had, gravity takes a certain amount away per second till it has none. And then gravity is pulling down. There's a moment where there's zero velocity. Then the velocity will start going in the downward direction. So it'll start small, then the next second it will get bigger, and then it will get bigger. When it hits the same height it started off with, it turns out that it's going to be going the same speed it was going when it was going up, but now it's going that same speed downwards until it hits the ground. So the ball is doing two different things. In the x direction, it just goes and goes and goes. In the y direction, it goes up and gets slower and slower and slower, goes to zero velocity, and then gets faster and faster going down. So the net result here, basically the ball can do two things at once. If it has a little velocity over and a little velocity up, we end up with an arrow like this blue one that goes at an angle. And the next second after that, the velocity up is smaller, but the velocity in the horizontal direction is about the same. So the arrow kind of points, not like that. The arrow kind of points at an angle that's not as steep. And then it's kind of the same thing. If all of the y, or most of the y vertical velocity's gone away, all the velocity is in the horizontal direction, right? And then the velocity starts to come back. It's got some in the horizontal direction and a little bit going down. Remember, vertical velocity is down is negative. So this would actually be a negative number there. And then the next second, it's going to be steeper. Kind of just like this. And you can kind of see if the velocity is doing that every second, then the end result that you get, if you throw a projectile, is a curved path. It kind of looks like this. It's in the shape of a parabola. My drawing is not beautiful. It's symmetrical, it goes up and then it turns around and comes down, and then the horizontal motion, it just keeps going and going and going. So that's the fundamental basics of projectile motion. So the question is, if we have a certain amount of initial velocity, we're shooting it out of a cannon, or in the physical lab, we usually use these little spring guns that shoot balls. We pull the lever, shoots a spring, the ball shoots. So we get to choose, it's adjustable, we get to choose what angle it's at. So the question they're asking you guys is, what angle do you choose to get at the furthest possible distance that you can? And you guys can see, as we talked about general projectile motion, both the x and the y matters. So if we decide to put all of our initial velocity, we shoot it straight up in the air, then what's going to happen to the ball? It's going to go up in the air, going to go pretty high. It's going to be in the air a good long time, but it's going to turn around and come right back down basically where it started from, right? What would happen if we chose to send all of our velocity horizontally? Well, it would start off, it would be traveling really well, but it would hit the ground basically instantly. Okay, so same thing, if it's a little above, and all of these arrows, the length of the arrow represents the size of the velocity, so they would be exactly the same length. So any trajectory, any initial angle that we choose that's mostly vertical is going to give us a really high trajectory that doesn't go very far. And any trajectory pick that's kind of mostly horizontal is going to go out, but is going to land really quick. So if we come up a little bit from that, we could get a little bit further. If we come up a little bit, we could get a little further. And if we come down from the vertical, say we started with this vertical with this tall trajectory, then we would have one that went up in the air And it turns out that it's symmetrical. Like if we have just a little bit off from perfectly horizontal and just a little bit off from perfectly vertical, they would land in the same shape, same spot. One would have a big high trajectory and the other one would have kind of didn't get very far, was going pretty fast, but hit the ground fast trajectory. So those ones would land here, those ones would land here, and there would be kind of a middle one that would land there. And it turns out that one isn't quite right. So there would be one there, kind of a long, narrow one. There's one trajectory that's ideal, that gets at the furthest that you could possibly get it with the energy and the initial velocity that you put into it. And that's the perfect one that we want to look at. Theoretically, that's what happens if you perfectly balance the amount that you put into the horizontal and the amount that you put into the vertical. And the way that you do that, you pick to put half of your velocity in each, is to choose an angle where half of your velocity is vertical and half of it is horizontal, which is 45 degrees. So if you're shooting from ground level and there's no air resistance, your hypothetical perfect angle of maximum, we use theta, Greek letter theta. My stylus is still dead. This is just the generic Greek letter for angles generally. So we say theta max is 45 degrees. So I'm not gonna like explain every little bit of your lab to you, but just think about it. If you have air resistance just kind of keeps your ball from going as far, but that's going to affect your perfect angle. If you're shooting it from an initial height, that gives you kind of a little extra oomph in your Y direction. It sets up a situation where if you shoot it horizontally, it's not going to just hit the ground immediately. That is going to change your perfect angle as well. So in the lab, you're going to do a few different trial runs. You're going to see what happens. And the data that you're going to graph is each of these different trajectories. You're going to write down how far it got and how long it was able to spend in the air. So how long it spends in the air is kind of proportional to how much height you gave it in the Y direction, but the overall length is going to be maximized when how much you gave it initial velocity in the Y direction versus how much you gave it in the X direction is balanced. And then the difference in the situations, whether you include air resistance, all of that is going to change that by a little bit. Okay, so just be aware, because we're not physically in a lab, you can do things like pushing a button and turning on and off your air resistance. And there's actually a question that you're supposed to answer about what happens when you do that. So actually check, do a couple trials with your air resistance on, with your air resistance off. Everything else stays the same. What does air resistance do? Does it actually change the perfect angle that you get? The other thing is you do get a question about whether mass matters. There's analytical equation-based ways that you can analyze whether mass matters or not, but you can also do multiple trials. You're going to get maybe different results with air resistance or without. So if your whole lab is done without air resistance and it asks you if mass matters, just do some trials at different masses and see what kind of results that you get, whether changing the mass changes the results. So basically, you just go through a few questions, and if it asks you, does changing one thing change your result, then you actually need to try it. And then a lot of what you do, you're supposed to turn in 2 different graphs. So that's why I gave you the tutorial on graphing at the beginning. Most people will get much, much better results if they use the spreadsheet. So that's why I showed you guys how to do that. It's actually quick and easy. If you do your graphing properly by hand, it's actually very time consuming. So you should find that it is much faster to do it on a spreadsheet, even if you are not familiar with spreadsheets. It's worth the extra minute to go in and be like, oh, how do you do this? And then do it. So that's why yeah.
I have a comment on that. So since I learned today how to use an Excel sheet to graph, I know that I'll be using that moving forward, but I did end up graphing by hand, and it is very time consuming, and I got kind of frustrated with it, but I went ahead and pushed through and did it. I ended up copying and pasting the graph that was already given in the worksheet or whatnot, or in the document, and I put it into Paint.
Okay.
And then I manually like plotted
So this
each
is what she's
point.
talking about. Can you guys see here? Like it gives you a little graph like this. Is that what you're seeing now in the Zoom?
Yeah.
Yes.
Yeah.
So yeah, thank you for your testimony. I'm sorry we didn't get the word out that you were allowed to do the spreadsheet in advance. Actually, I do think that I made an announcement back at the very, very beginning that you guys are allowed to use graphs, spreadsheets for graphs, but I just updated that today. So everybody who's doing this right now gets the word. So
And
thanks.
so I ended up just copying and pasted like the completed graph that I came up with into the lab, and I uploaded into the system. So I'm hoping that you'll be able to see it.
Okay. Yeah, and thank you. Also, I do think you sent me an email about that, and I can log in to your submission and make sure that I can see it. That should work fine. As long as the files are imported properly, any way that you want to do it is fine. And then just a note for next time, if you want to submit your graphs just as a separate file, the system will accept multiple file submissions. So upload, if you want to upload, if you leave all of your written data in one format, submit that. You can also submit your graphs separately in whatever data file that you use. And that should make it a little bit easier. Does that help?
Yes, thank you.
Okay, and this will actually be really good in the future. This keeps coming up. Most of the labs have some kind of graphing to do with them. So if it feels a little frustrating this time, thank you for your time investment, but that whatever you do now will help you in the future. You'll be quicker and easier and hopefully not at all complicated.
Okay.
Any other questions, concerns? Okay, I will go ahead and stop the